Charge distributions. It's not the 29th, but when I updated the slide, it was the 29th. All right, it's 31st. Electric field of a dipole. You have addressed dipole stuff in chemistry, polar molecules and all that jazz, so this shouldn't be entirely new. Anyways, we have this dipole, okay? And the big idea is that there is some distance, a small distance, S, between the centers of charge, if you will. So in a polar molecule, we're talking about the nucleus versus an idealized electron, say, in the cloud. That would have some distance separation between those two things. So this is a noteworthy slide for note taking because it's the basics of a dipole. And if you Googled electric dipole, you get this same basic idea from everything that's out there on the interweb. The big idea is that S is insanely smaller than the distance from the middle of the dipole to the source of the field. All right? That's the basic idea, which we'll see. This totally saves the math problem at the end because the complexity algebraically of this interaction between S and R gets ugly for a while, and then it ends up being the relative size ends up being a bonus. All right, so a dipole looks like that, and it is these charges get stretched because the plus charge wants to go in the direction of the electric field, whereas the minus charge wants to go against the electric field. Hence, the dipole gets stretched. If the electric field's strong enough, it could conceivably rip it apart. That would be a huge electric field, by the way. And then S would be more like R. You don't have a dipole no more. So that's the thinking. Now, this is where I wouldn't bother taking notes unless you're a physics major, which none of you are physics majors. So just let's think through this line by line. So there is the negative end of Q2. There's a position vector, okay? And so there is some position X at the end of things, and then the midpoint between the two charges of the dipole. So the position vector for the negative end of the dipole is the X position at the end minus the halfway point. And if this is since we picked it to be on an X direction, that's all I have to pay attention to here. So this vector, this position vector, has a magnitude. I literally just take this thing, plop it into here, square it. Of course, it has no other parts, so the square root of something squared is just that thing, right? That is right here. Which isn't surprising that the length, because that's what the magnitude of that position vector is asking me, how far away is it? Well, if x was 1 meter and s over 2 was half a meter, it'd be half a meter, or 1 minus half. Or in this case, since it's a general and I don't have any particular values, it's the x position minus the midpoint of the dipole, which I've labeled s over 2 because s is the separation distance of the two charges, and x is the source of the field. All right. Then the rest of this math, I want a unit vector. Okay, take the vector, divide by its magnitude. Guess what I get? I get this really interesting and nice to work with unit vector. All right. And it's telling me that it's pointing strictly x, which we knew because that's the way we set it up in the picture. We do this to make our life easy in physics. We pick an ideal, super duper simple, we work it out. And so that means if I wanted to, just pretend that you want to, I could define the electric field at the negative end uh, of the dipole in the classic way. This is just, the Coulomb constant times charge over distance squared. This is just r. All right. Top thing squared with its pointer, the unit vector, and I could define the electric field from the negative end this way. Yay. What good will that do me? That'll be fantastic if you have to tell a computer to do this for you, such as if we were making Python code. We'd absolutely want to be able to enter it this way as a vector. And this vector would have a magnitude. This right here is a magnitude. The toy on the inside here, that is the magnitude of the electric field on the negative end. That's all that is. None of that math that's still basic algebra. It may be tedious to write and look at, but it is just still basic algebra, right? So that's the negative end. Yay. Look back here, it was minus on the inside, and the positive end, oh, who knew? The math would be the same, except I'll get a slightly different answer. Okay. So if you want to go look at this on YouTube later and pause it, and show it to your friends and relatives and say, look what I did in class today. Yeah, go for it. But we get the other end of the field. And it has the exact same structure, only an x part, but there's a plus here. So minus q, here it's a plus q, and it's plus on the inside. Okay. Simple. So I'm not going to re-explain that. It's just doing the same stuff to the other end of the molecule. All right. In order to have the whole field, we have to add up all of its parts. Sum of the parts equals the whole. Parts, the whole. So that idea keeps coming back. You knew it before college. Still is important. We add all this stuff up and we get this wondrous. I know that you're just like, oh man, that's so dang awesome. Look at all that. Hold your applause, please. I know you can hardly contain yourself. It's just like, you feel like a 13-year-old at a Justin Bieber concert. You just can't hold it together. Yay, I have the whole field in a vector form. Congratulations. Now, we imposed this thing. This is only x direction. Not because the dipole can only be in the x direction, it's because that's the way I modeled it. So again, not knowing exactly how far and wide you will reach in your scientific career, this whole modeling game in science involves picking a super simple, idealized situation, get it as simple as you can, and then bring the rest of reality in. That's the way it works. Because if you try to do too much at once, you just get lost in the weeds and they'll never find your body. All right. So but they'll find the trash you left behind. All right. It is true a dipole can be oriented in lots of ways. Obviously, it's not like polar molecules have to stay on the x-axis only. Like, everybody knows better than that. So I have to generalize. So instead of x, I'm going to go with r. So now I went from a very specific to a general case. Because now r is going to be this position vector that can be along any direction. In fact, it could be y, it could be z, be all the above, right? But notice the equation doesn't change much. Also, important thing is, here's where the constants are. Coulomb's constant is not going to change, and the amount of charge isn't going to change. But the separation distance of the polar ends of this thing could change, and obviously the r distance to the source of the field, that's also something that can change. One reason that I don't mind showing this to you, and even though I'm not going to test you on the derivation, I mentioned this earlier, and as we move forward in the course, we can get more specific about how medical imaging technology works, which is material to your life sciences. That's what this course is for. Obviously, in something like an MRI or a CAT scanner, or you name the medical imaging device that's deploying electromagnetic waves to get pictures of what's on the inside of your body, guess what's changing? These polar molecules are being torqued all throughout your system. To some degree, they're being stretched. Of course, those machines aren't measuring the length S. We're assuming a standard fixed polar distance, if you will, and we can count on that. But the distance from a particular spot inside your body and the imaging device, that will constantly be changing. That's the R value, if you will. So you've written Python code and put equations, vector equations, this is a vector equation, into it and had it produce motion, moving things. Reverse engineer that. That same kind of code, some engineer put into the box that controls the imaging device that's connected to the sensors that's receiving the feedback from blah, blah, blah. All right. And somewhere in the code of these things would be something very much like this, if not exactly this. Anyways, moving on. We go through a bunch of rigmarole and we obtain a magnitude equation here in blue. So try to just keep your attention on the blue highlight while I yap about it. Ends up being the case that the magnitude of the field, obviously we already knew it was directly dependent on the charge. We knew that. That's basically Coulomb's law. Ends up being the case, and it makes sense that the separation distance of the dipole, as that changes, you'd expect the field strength to change, and obviously the r distance is going to be material to that. And then it's getting divided by, wow, it's a double inverse square. Wasn't expecting that. Okay. But I have two directions that I'm dealing with, the S direction and the R direction. So that's where what I really have here, one way to think about this is it's sort of like, this is the inverse square for the S part, and this is the inverse square for the r part. We could think of it that way, okay? I don't think that's technically correct, but figuratively correct, all right? So don't take me to the bank on that. And if you're watching this on YouTube and you're a real physicist, remember what I just said, all right? Now, here's what I was pointing to earlier. This fact right here, if R is much, much greater than S, that's what the double inequality symbol means. When you have two of them together, it means much, much of that. That's our math lingo. So the distance, you would expect that the distance between the dipole itself and whatever the electric field that's influencing it to be a much, much greater distance than this tiny angstrom level, less than a nanometer separation between the ends of a dipole. Well, if that's the case, if R is much, much bigger than S, well, then these things just sort of goes to zero, really, essentially what's happening here. So that means I get to swap all of this right here, gets to just go to R squareds. I really love this app because the colors are so nice. It doesn't work as great in an ITV room because the projectors stink in there. But on a real screen, these colors pop real good, all right? So all of that math that we thought would be excessively ugly and whatnot actually ends up working out kind of nice for us. Of course, this R here will kill one of these R's here, leaving us with an R cubed. And so at the end of the day, the electric field, this is something that inevitably you'll need to use in a computation. So if you have been itching to take a note, this is something that we'll need. Is everybody familiar with that double pipe next to dipole as meaning parallel? It's a little geometrical symbol. The electric field parallel to the dipole axis, meaning if I have a plus and a minus in a dipole, that's the axis. So it would mean that we are talking about something that is running parallel to that axis. Has this relatively simple equation. The only difference that it is from a normal electric field is that now I have, let's highlight the difference here, 2 and this extra dimension of length were not in our original thing, and then it was squared. But now we have an additional length measure in the top and the bottom. So it's a dipole axis has an inverse cubed pattern, whereas a regular electric field between 2-point charges is an inverse square pattern. How much will that matter to you in real life? Probably not much, but on your homework, using the right formula will matter. Because guess what? We have dipoles, and we can talk about the field parallel to the dipole axis, or we can talk about the field perpendicular to the dipole axis, which is what I said will be shown next. So this is a noteworthy slide because it's a summary slide. We just showed this. If I were to go through the same rigmarole with the perpendicular part, I would obtain this, which is very much like the parallel one, except for the 2. And that just is a feature of the math. And the important thing, as always, is assuming that the distance, the source field is much, much farther away than the two ends of the dipole are from one another, then this works. If that is not true, these equations flop and you go back to the normal electric field mode. We'll have a lab where we sort of just kind of notice that. We'll play with separation distance and see how it affects fields.
When it says Q is the magnitude of one of the two charges, is it talking about like the source field or like either end of the dipole or?
Well, a dipole automatically they're equally charged, right?
Yeah.
So you just need Q is just one of the charges. That's all it is. Yeah.
So one end of the dipole.
Yeah. So let's see how this works out in the math, or for a, or how we like to point things away. All right. Let's, we like to make this convention here. The orientation of the dipole, which way is the dipole pointing? So we sort of saw this a little bit the other day in one of our kind of clicker quiz type questions, because we were letting it get torqued. We direct it away from the negative charge to the positive charge. All right. And as we play more with this, that'll become more obvious, but do attempt to give a reason here. And the reason for this is the fact that the dipole will tend to orient itself, be torqued, if you will, in the direction of an external field. So guess what? The positive charge is directed along the electric field. So that's why we have it go from the minus to the plus. We're forcing that sort of pointing towards the plus end. And it is a convenience matter. That just works well with everything else we do in physics. Could we gone the other way? Sure, we chose not to. So there you go. And that definition, that's for reference. We'll move on. All right, finally, an example. It's always good to have an example. Dipole and a charged ball. So this dipole, and I think I have a pretty picture of this coming up on a slide. Can't remember. Has 2-point charges in it, +4 and -4. And separated by a distance of 2 millimeters. And we're given this position. So it's in the XY plane, because I have non-zero X and Y parts and a 0 Z part. So flat on paper kind of picture. And then the hollow plastic ball has its radius and charge distributed over its surface, and its location is also in the same plane. So we have two charged objects in the same plane at different locations, and we'd like to know what is the net electric field at some other location. Why did we choose that location? Well, that's as everyone knows, that's where all the cool kids are, at that location right there, 0.03, 0.040. That's where the cool kids are. So we want to know what's the field at that location. Totally arbitrary. Just totally arbitrary. Now, you probably don't think that's as simple as it is. But the superposition principle tells me that if I want the net of anything, It's just going to be the sum of all the things that are interacting in that system. And in this system, all we have is the electric field that's produced by the dipole, and we have the electric field that's produced by the ball. Period. So I add them up. That's what the superposition principle tells me. The sum of the parts equals the whole. That's the net effect. We did a boatload of that in first semester, all that force summing according to Newton's second law. And that doesn't change at all. So the big idea is here, superposition principle, and then all of those parts bust out into the math that follows. So that's the thinking behind it. So one of the things that you can do is you just one at a time, what are the things that I need? Well, if I'm talking about an electric field, I'm already given the charge and the separation distance, but I'm not quite given the magnitude of, I'm not given the length from the dipole to the ball. I'm given vector information, which requires a computation in order to obtain what r is, because it's a magnitude. So the first step is going to be figure out what's the magnitude of this distance. Okay? So this is the uh, uh, let's remind ourselves. So this right here is coming from there, and this right here, those are the parts we're dealing with right now. The distance from location C to location A. C, A. One thing at a time. So we do that math. It's parts is parts, and we get the magnitude is 11 centimeters, or 110 millimeters, if you will. So that's a much bigger than S. So we run with it. So that's just a test of what I was showing earlier, that these dipole rules work when something's much bigger. So now it's plug in Chugsville. I have R. So my R value is obtained. It's this. And I put it into the equation for parallel to the dipole axis. How do I know it's parallel?
Symbols on each bonds, dipole axis, and parallel symbols is the y position.
The Y position's what's different. Okay. So I get a number. Yay, 108. That means I have part of that piece of the puzzle. All right. So here's I guess a picture uh, uh, of how this might look. So our dipole up here, our ball over here, and our observation location here. The dipole, the direction of that field has to be towards the plus thing. That's what we defined earlier. All right. The charged ball, it has a negative charge, if I recall, so therefore the field's going to be pointing towards it. That means our net is somewhere in between. So just conceptually, If we lay it out according to the positions given in the problem, our expectation is a positive outcome for the net effect here. All right? Wherever it is, I'm going to have an x part, and I'm going to have a y part on that net equation. So now I have to do the position vector for where the ball is at. So again, this was the observation location. This is where the ball is at. Hence, the position of the charge ball relative to observation C is going to be that. That's a vector. Guess what I can do with that? I can find its magnitude by taking the square root of the sum of the squares of its parts. I can take that value and divide it into each one of its parts, and I have the unit vector. Just, it's arithmetic, low-level algebra, which way back here, coming next. Magnitude, dump those into here, and out you get a magnitude. Picture, you want a unit vector? Take the vector itself that we got from up here, divide it by its magnitude, each one of those parts, and you get a unit vector that looks like that. All of these things go into the making of you got to have a magnitude and a unit vector, magnitude and direction, in order to do the computation. So there we go. We take all of this magnitude stuff, okay, and we jam it in there. So here's that was the magnitude. Okay, I think that was supposed to be cubed there. In that one. So we plug in Chugsville, and we get this vector thing that has an x and a y part to it, which is unsurprising given that's all we had to begin with was x and y parts. Plus we knew, if you think back, so those are my x and y parts, yay. And I think we were one. The magnitude. No, we wanted the whole thing. So now we add them. This is the one that we computed first. That was the dipole. This is the one we just did for the ball. So the net will be that. If you take a 0 and add it to a 57.2, you get a 57.2. If you take a 108 and a 78.7, you get roughly 187. That's all we got there.